In this video, we take a look at domain and range of functions. We saw in a previous video that a function is a relation where any single input can only respond to one output. In other words, if I put in a number, it cannot go to two different places. We know the set of inputs is called the domain, and the set of outputs of the function is called the range. So if we take a look at these two finite functions, we can identify the domain. Again, we have ordered pair notation here on these finite functions. You'll notice in this first function, we have inputs of 1, 2, 3, 4, and 5. And our outputs are 2, 3, 4, 2 again, and 3 again. On the second function, our inputs are 0, 1, 2, 3, 5. And our outputs are 0, 1, 5, 6, and 10. Let's write that down. When we are writing the domain of any function, the domain is the set of inputs. So generally speaking, we put set brackets around the elements of the domain. Like I said, in this first function, since it's finite, we can just list the inputs 1, 2, 3, 4, and 5. So the set containing 1, 2, 3, 4, and 5 is the domain. On the other hand, the range is the set of outputs. And we can do that. Again, we write those in set brackets. Our outputs are 2, 3, 4. And we have a 2 and a 3 again. When we're talking about a set of numbers, we do not have to repeat those numbers. So I don't have to rewrite 2 and 3. I can just rely on 2 and 3 from the previous ones. So hopefully that makes sense. But this is the idea. Maybe spacing, I'll make a little bit nicer look to it. So the domain is the set containing 1, 2, 3, 4, and 5. The range is the set containing 2, 3, and 4. Now, technically, we don't have to put the numbers in order. So in this first one, the domain, I could have put the 5 in front if I had wanted to do that. But generally, when we write it down, I write them in some sort of order, either the way they show up or just numerical order. But you don't have to. On this second function, we already said what the inputs were. So the domain is 0, 1, 2, 3, and 5. Again, put that all into set bracket notation. Range is the set containing 0, 1, 5, 6, and 10. So that is the domain and range for these finite functions. That is, functions with finite number of ordered pairs or a finite number of inputs. So the natural progression from there is to say what would happen if our functions had an infinite domain. So what if our functions were outputs were defined by an expression. In equations or function notation, usually we can plug in almost anything that we want to. There are some restrictions, which we'll see in just a second. Now, when we're plugging in numbers into functions and we want to graph on the Cartesian coordinate plane, we want real numbers to be plugged in, and we want to also get out as our output real numbers. We don't want to get things out that are complex numbers or imaginary numbers or anything like that. So how does this work? Well, because we want real numbers, we want things to be well defined. And there's a couple of instances where we commonly get some domain errors. Specifically, if I plug in a number and the expression forces me to divide by 0, or if the expression forces me to take the square root of a negative number, then I'm no longer on the real numbers. When I divide a number like 4 by 0, then that expression is undefined. When I take the square root of a negative 4, for instance, that is undefined on the real numbers. We'll talk about imaginary numbers later, but if I want to graph something, I don't want to have square root of a negative number. If I want to graph something, I don't want to divide by 0 since that's undefined. By the way, just as a little side note, dividing by 0 is undefined. There are realms of mathematics where they force dividing by 0 to become infinity, but we're not going to do that in this class. So let's take a look at 3 different functions, and let's find the domain of these 3 different functions. What can we plug in? In this first function, we have f of x equals 4x squared plus 5x minus 6. And you'll notice that any number I plug in, I can square it. Plug in any real number, and I can square it. Plug in any number, I can multiply by 5. So there's actually no problems here where I'm going to encounter one of our common domain error situations when I plug in a real number. So that means that the domain here is all real numbers. Now, just as a note, the domain is all real numbers. We're not going to go over the range right now. The range is a little bit more involved. The range technically is not going to be all real numbers, but it's going to be all real numbers bigger than a certain value. But we're focused on the domain. What can I input? And the answer is I can input any real number that I want. Now, all real numbers have a variety of ways of being written. Here, I just wrote out the phrase all real numbers. You'll often see a script R with all real numbers as well. You can also see something like this. X can be anything from negative infinity to positive infinity. That's another way to write all real numbers. You can also see the script R that some people will write as well. Let me go find that. There it is, the R with a double slash. Sometimes when people write this, they'll write a double slash on the right side and then just the letter R like that. Usually with the when you write this by hand, 2 slashes on the left with an R. That's how you write it by hand. The script that this Word document is giving me looks like this. It's a R with basically double slashes, excuse me, double lines around the whole thing. So anyways, that's all real numbers. So if you see that symbol, or if you see a handwritten symbol with a double slash on the left-hand side, that's all real numbers. Now let's take a look at these other two functions. And let's look at the domain here. The common domain errors that we're going to see in this class are going to happen when we divide by 0 or when I have a square root of a negative number. Well, 2x plus 12 divided by x minus 5 is not going to have any problem with square roots in it. However, we could divide by a negative number when our denominator becomes 0. So in other words, we're going to have a problem when x minus 5, our denominator, is equal to 0. So we have a problem when x is equal to 5. And if you think about that, what's going on is that when you plug in 5, you end up with 22 over 0, which is undefined. So what does this mean the domain is? Well, there's no other place that we're going to divide by 0. So the domain is all real numbers, excuse me, except for when x is equal to 5. So it's all real numbers except when x is equal to 5. Here, obviously, I use the symbol for all real numbers. You can write out the words all real numbers if you want. But that's it. That's the whole thing. Now, that's the only problem because that's the only spot in which we're dividing by 0. It's pretty clear to see we've solved this equation. And so therefore, that's the only spot where our denominator is 0. Let's look at this next equation here, or not next equation, next function. So this next function is the square root of x minus 11. The expression is the square root of x minus 11. Well, there's no denominators here, so dividing by 0 is not going to be a problem, but square root of a negative is going to be a problem. So what we would do is we'd approach this in one of two ways. We would say either this, we have a problem when the thing underneath the square root is less than 0. Or you could also say that this only works when the thing underneath the square root is greater than or equal to 0. Either one of those options makes sense. It's going to give you the same thing. So there's a problem when the expression under the square root is less than 0, so that's negative. Or it's perfectly fine when the thing underneath the square root is greater than or equal to 0. I'm going to use this right-hand one that it only works when x minus 11 is greater than or equal to 0. So works when, and then what I can do is I can add 11 to both sides. Adding 11 to both sides does not change the sign. So it works when x is greater than or equal to 11. And that's my domain. So my domain is all x such that x is greater than or equal to 11. All right. So that's how that works. Now you can phrase this in different ways. The domain is all x values such that x is greater than or equal to 11, or the domain is all real numbers x such that x is greater than or equal to 11. Um, so you can phrase these in different ways, but we get the concept is that all values which are 11 and higher are in the domain, and any value that's less than 11 is not in the domain. Let's look at another example of three functions and find the domain of these. If you want to try these on your own, obviously push pause on the video. I will do these in just a couple of seconds. For the function f, we have cube root of 2x minus 12. Now, here's the thing. Square roots can't have negatives underneath unless I'm dealing with complex or imaginary numbers. But cube roots can have negatives underneath. In fact, we'll see the graph of cube root functions a little bit later, but the negative times negative times negative gives me a negative. So it's perfectly fine to do cube root of a negative number. For instance, cube root of -8 is just a -2. So it is perfectly fine to have negative values underneath a cube root, and that means that the domain here is all real numbers. Okay? Or you could have used the symbol, that R symbol, for all real numbers. So could have used just the shorthand R. Let's take a look at g of x. Well, here we're going to have a denominator which could turn into 0, possibly. There's no square roots, so our denominator turning into 0 is the problem spot. And what's happening there is I have a quadratic function set equal to 0, or not quadratic function, a quadratic expression set equal to 0. Most people have factored before who are watching this video. So I'm just going to do a very quick factoring lesson. Basically, if I have a 1 in front of my x squared, I know that I can factor into x, it's going to be plus or minus something, times x plus or minus something. The two numbers in here are going to have to multiply to give me negative 15 and add to give me a positive 2. So they multiply to give me negative 15 and add to give a positive 2. Those two numbers are going to be a positive 5 and a negative 3. 5 times negative 3 gives negative 15. 5 plus negative 3 gives me a positive 2. And then we use what we call the zero factor property to solve. So we say that either x plus 5 could have been 0, or x minus 3 could have been 0. Solve each one of these separately. X could have been negative 5 when I subtract 5 from both sides, or x could have been a positive 3. So if I plug in negative 5 into my function, I'm going to get a 0 in the denominator. If I plug in 3 into my function, I'm going to get a 0 into my denominator. Now be careful. This does not mean that the domain is just negative 5 and 3. In fact, that means the opposite. The domain is all real numbers except when x is negative 5 and when x is 3. There's different ways to phrase that, but the domain is all real numbers except when x is negative 5 and x is 3. Or sometimes people will say the domain is all real numbers except negative 5 and 3, and they won't write the x equals part. But there you go. So that's basically factoring a denominator and then setting both pieces equal to 0 because we have a problem when that denominator is 0. The last function this example has us deal with is my function h of x is equal to the 6th root of x plus 10. Now this 6th root is an even root, and therefore, just like a square root, we can't have an even root of a negative number. It's perfectly fine, like we saw up here, to have a cube root of a negative number. But a 6th root of a negative number will not work either, just like the square root. So even roots of negatives don't work. And therefore, for this function to work, it only works when our argument inside of that 6th root is greater than or equal to 0. And in this case, that means x has to be bigger than or equal to negative 10. Subtract 10 from both sides, and that's what we end up with. So that's the domain. Domain is all real numbers such that x or all x values such that x is greater than or equal to negative 10. Again, even roots like a square root, a fourth root, and a sixth root, we can't have negatives underneath. Odd roots like a third root, a fifth root, a seventh root, those I can have negatives underneath. Be careful about that. But there you go. That's how we can find the domain using some algebraic know-how. Now, many times when we're dealing with a set which has infinitely many numbers, we like to have some notation that goes along with infinitely many numbers. And in fact, there's a few different notations that we could use. We've seen some of the algebraic notation that says like x is greater than or equal to negative 10, or x is greater than or equal to 11, or you could have done x is less than or equal to 11. But there are two other notations that we'll look at right now. There's something called an interval notation and something called a number line notation. A number line is just drawing our domain on the number line. It's graphing a solution on a number line. Now, we're going to generally graph the domain in this section, but in general, you can graph any type of infinite set on a number line that you want. It doesn't always have to be my domain. Could be your range, could be any other thing. Interval notation uses parentheses and square brackets to show the solution. And in short, parentheses means that the value is not in the set, and a square bracket means the value is in the set. I can do some of these things with the functions that we just looked at. So let me do that real quick for the functions we just looked at. All right, so let's take a look at this last one we did, where we had f of x is equal to the cube root of 2x minus 12. We said that the domain was all real numbers. If the domain is all real numbers, then we can algebraically write that in a few different ways, but usually the most popular is to say that x is somewhere between negative infinity and positive infinity. All right. Now, that's just like the algebra equation way to write things. So algebraically, x is anywhere between negative infinity and positive infinity. On a number line, that's what I have right here, this number line. The way we would do that is we draw some sort of arrow, and we'd make sure that our arrow goes both ways. It goes across the entirety of the number line. Some people would shade this in a real thick manner. Other people would shade this in a less thick manner. But I tend to make this just a single line right on top of the number line and say, well, we go forever to the left and forever to the right. This number line essentially represents the x-axis. So that's the number line notation. Now the interval notation is going to give us the bounds of what the domain is. So on the left-hand bound, we get negative infinity. Now, negative infinity is not a real number that we can touch. That's why we didn't have the equal to sign there. So because it's not a real number that we can touch, when I write negative infinity in interval notation, I'll use parentheses right next to it. So interval notation says that I can go from negative infinity up to positive infinity. And because I can't touch either a negative infinity or a positive infinity, I'll put parentheses around the whole thing. That's interval notation. So we see our algebraic notation. Some people would just say algebraic notation. Then the interval notation, and then the number line there. So that's when we have all real numbers. Now, what if we have something else? What if, for instance, we look at this, where the domain was all real numbers except when x is equal to -5 and x is equal to 3. Now, algebraically, we can rewrite that. It's basically everything except that x cannot be equal to -5 and x cannot be equal to 3. So the not equal to symbol looks like an equal to symbol with a slash through it. Let me do the number line notation before we do the interval notation. So what would happen on a number line is we designate a spot for -5. Let's say that that spot represents the number -5. Whoops. And we designate another spot which represents the number 3. Now, everything except for those two spots will work. When I can't touch a number, I put an open circle around it. That's the traditional way of saying that we can't touch that number. Our graph doesn't hit that number. And then I would say any other numbers do work. So I'd shade in between the -5 and the 3. I'd shade below -5. I'd shade above 3. So every number except for those two will work. Notice that this splits our number line into 3 different sections. And the interval notation is going to reflect that. So the interval notation would say anywhere from -infinity up to -5 will work. So anywhere from -infinity up to -5, that'll work. I cannot touch infinity because that's not a real number, and I cannot touch 5. So that section from -infinity to -5 will be there. The next section goes from -5 to 3, and anywhere between -5 and 3 also works. Again, I can't touch -5 and -3 because that's the not equal to spots. And then anywhere from 3 and above will also work. Again, can't touch 3, can't touch infinity because we have this open circle around 3, and infinity goes forever. And then usually what happens is you just write, this is a mathematical union symbol that I'm writing in there to show that all three of those are in the domain. That's a pretty complicated domain. That's more complicated than anything that we're really going to be focused on. So 3 sections, and they all are smashed together. We have parentheses with every number because we can't touch the 3, can't touch the -5, can't touch infinity, can't touch negative infinity. But there you go. Let's look at a more straightforward one, and that's the next function. H of x, we saw that the domain was all real numbers such that those numbers are bigger than or equal to -10. Now, the algebraic notation is just the equation itself. That is x greater than or equal to -10. I'll do interval notation in just a second. And then obviously the number line we have written here. So for the number line, what we would do is we'd make a mark where -10 is. And then because we can touch -10, we'd draw a circle and we'd fill it in. Obviously, in this, what I'm doing with annotations, it's kind of hard to fill in completely a circle. It's a little bit easier to do with a pen and pencil. So a filled in circle means I can plug in -10. And then any number that's bigger than -10 is going to work. So I put an arrow to the right of -10. That would be the number line notation. Now the interval notation, there's only one section that works, and that goes from -10 and up. So the interval notation would start at -10 and go up to infinity. Infinity I don't touch, so I put a parentheses, but -10 I can touch, so I put a square bracket with -10 on the -10 side. So my interval notation is square bracket, -10, comma, infinity, parentheses. Again, that's because I can plug in -10 and have it work. And then I can't plug in infinity because infinity is the idea going on forever. Infinity is not a real number. So there you go. That's the entirety, oops, of the interval notation and the number line. So we see that for some functions, like these ones here, like the functions we saw in example 2, for those types of functions, we had to restrict our domain because we ended up with non-real numbers as our output or an undefined output when I plugged in certain things. You can also just force your domain to be restricted. And we can restrict our domain and range bounds on a graph if we want to. It works kind of like the number line that we just did. Closed circles indicate where a graph hits a point. Open circles indicate where a graph does not hit a point. So if I look at a graph with a restricted domain, a restricted range, I should be able to visually see these closed circles, these open circles, and determine what the domain and range of that graph was. So let's take a look at this graph and let's find the domain and range for this one. Obviously, there'll be more to come, but let's force ourselves to look at this one. So you'll notice that, again, the x-axis here is traditionally my inputs. The y values are traditionally my outputs. The x values, this graph is restricted from x values of -2 up to an x value of 3. So the x values go from -2 to 3. They touch -2 because that's a closed circle. It does not touch 3 because that is an open circle. So that tells me that the domain goes from -2 to 3, doesn't touch 3, but does touch -2. What about the range? Well, the range, it looks like the lowest y value is a y value of 1. And then all of the y values get hit up until we end up at 10. And since there is a closed circle at 10, it looks like it gets hit at 10. Now, by the way, even though there's an open circle here at 5, there's also a point over here which has y value of 5. So the y value of 5 is being reached just by this point, not this one. So that tells me that the range goes from 1 all the way up to 10 and looks like it touches 1, looks like it touches 10. I'm going to write the domain and range in two different ways. Again, the domain we're seeing goes from -2, it touches -2 up to 3, and it does not touch 3. So the algebraic notation says x is between -2 and 3 and can be equal to -2, not equal to 3. So that's the algebraic notation. In the interval notation, we'd say, well, it goes from -2 up to 3. Since we cannot touch 3, we put a parentheses at it. Since we can touch 2, we put a square bracket, -2, we put a square bracket at -2. So square bracket on -2 because we can touch it because of the closed circle. Open bracket or parentheses at 3 because of the open circle. The range, again, if I'm doing this in algebraic notation, I'd say that the y values go from 1 and up to hitting 10. In interval notation, since we can hit, it looks like we can hit 1, and it looks like we can hit 10. We know can hit 10. That's a closed circle there. Our range goes from 1 up to 10 with square brackets on both sides. Can hit 10, can hit 1. Hopefully that makes sense. Domain is the x values that can be obtained. Range is the y values that can be obtained. Let's try the same thing for this graph. If you want, push pause on the video and try it on your own. I will write down the answer in just a couple of seconds. All right, once again, I'm going to go from algebraic notation and interval notation. So our x values looks like it goes from -2 up to +3 again. I cannot touch -2, but it looks like I can touch a +3. So in this case, we're going from x values between -2 and 3, being able to touch 3 but not -2. That means the interval notation would be parentheses, -2, comma, 3, square bracket. The range, well, the bottom of the range is clearly -4. We have one point there which cannot be touched at -4, but our other point does touch the -4. So our y value can touch -4. And it looks like the highest point is 2.25 or 2.25 is what the graph looks like. If you notice this graph, we're somewhere between 2 and 3 at our highest value. It looks to be about 2.25 based on the grid. So that's what I'm going to say. The range is the y values go from -4, can touch -4, and it looks like we can touch 2.25, 2.25 up top there. And so in interval notation, we'd have square bracket -4, comma, 2.25, and then a square bracket. So x values give me my domain, y values give me my range. Closed circles mean I can touch it. Open circles mean that I cannot. Let's do one more example. Here we have example 6. Let's find the domain and range for this graph. Once again, push pause on the video if you'd like to do it on your own. And in a couple of seconds, I will do it on the video. On this graph, it's fairly straightforward. The x values are going between -2 and +2. Since we have a closed circle at -2, our x value can touch -2. But we have an open circle at +2, so my x value cannot touch +2. That means if I'm doing interval notation, it will be square bracket, -2, comma, 2, and then parentheses. So that's the interval there. The range, again, that's the y values. The y values go from -4 up to +4. In this case, -4 we can touch because we have a closed circle, but +4 we have an open circle. So that means that -4 we can touch with the y value, +4 we cannot touch. Interval notation would therefore be square bracket, -4, comma, +4, parentheses. And that's it. That's the whole thing. So we see in a number of these cases how we can get graphs with restricted domains. In other words, if somebody just arbitrarily restricts the domain, then we can do that. We can see that on the graph. Now, the last part of this section is going to be dealing with piecewise defined functions. A piecewise defined function is a function whose output values are determined differently by what number you plug in. So what that means is the function expression is broken into pieces depending on parts of the domain. So if x is at a certain place on the domain, then our output is going to be determined one way. And if x is at a different part of our domain, our output is going to be determined another way. It's called piecewise because we could have as many pieces as we want for determining the output values. Let's look at an example. Here we have a function f of x, and it says the function f of x is equal to x minus 5 for x values that are less than 2 and negative x squared for x values which are greater than or equal to 2. In other words, if we plug in a number which is smaller than 2, we use x minus 5. If we plug in a number which is greater than or equal to 2, then we plug it into negative x squared. Let's find some output values here just to drive that point home. We'll find f of 2, f of -4, f of 0, and f of 11. When I plug in 2, since 2 is in the part of the domain where x is greater than or equal to 2 specifically, I use the output value of negative x squared. So what I do is I take -2 squared, and that gives me my output. The negative is on the outside of the parentheses here, so I get a -4. When I plug in -4, well, -4 is on the part of the domain where x is less than 2. So in that case, I'll use x minus 5 as my expression to plug in. Therefore, I'd put in -4 minus 5. So my output in that case would be -9. So whenever an x value input is less than 2, I use x minus 5. Whenever my x value is greater than or equal to 2, I use negative x squared. Let's go to 0. Well, 0 is less than 2, so I use x minus 5. Plug it in. 0 minus 5 is -5, and then we're done. If I wanted to do 11 as my input, 11 is bigger than 2. So I'm going to be using the negative x squared, which means negative 11 squared is what I need to evaluate. That negative is on the outside of the parentheses, so I get a negative 121. This function is piecewise, and usually the phrasing we say is that it has two pieces because there's two parts of our domain here. The part where x is less than 2 and the part where x is greater than or equal to 2. Or in other words, there's two different output functions. So I say this is a piecewise function and it has two parts to it. Not all functions that are piecewise have to only have two pieces. Here is a piecewise function with three parts to it. H of x is equal to 8 when x is less than or equal to negative 1. H of x is equal to x squared when x is between negative 1 and 2. H of x is equal to 2x minus 5 when x is greater than 2. So here we have a piecewise function with three pieces. Notice, by the way, sometimes it'll say when x is a certain range. In the previous example, it said for x in a certain range. Sometimes it'll say x minus 5 if x is a certain range. So there's different linguistic things you can use. So you can use when or if or for as my word there. But the concept is all the same. If x is in a certain range, you use this output. If x is not in a certain range, a different range, use another output. Let's calculate some output values here. H of negative 4, H of 2.3, H of 7, H of negative 6, H of 2, and H of negative 1. Let's do these calculations. So H of negative 4. Now, negative 4 is less than or equal to negative 1. So the output value there is simply going to be 8. So that's pretty straightforward. H of negative 4, anything that's less than or equal to negative 1 gives an output value of 8. How about 2.3? Well, 2.3 is greater than 2. So since it's greater than 2, I use the 2x minus 5. 2 times 2.3 minus 5 turns into a negative 0.4. Or just negative 0.4, however you like to write that. 7 is also bigger than 2. So since 7 is greater than 2, I'll use 2x minus 5 again. That's 2 times 7 minus 5, which is 14 minus 5, which is 9. When I deal with negative 6, well, negative 6 is less than or equal to negative 1, so the output value is going to be an 8. When I plug in a 2, well, 2 is right on the edge, and the one I have to use when x is equal to 2 is the middle one, that's the x squared. So I plug in 2 into the x squared, I get 2 squared, which is equal to a positive 4. Negative 1, well, that again is right on the border. I have to use where it's equal. So this is when x is equal to -1. When x is equal to -1, the output value is 8. So we can see that for some values, we end up with 8. For some values of x, we have to plug into the x squared. For some values of x, we have to plug into 2x minus 5. Again, this is the essence of what a piecewise defined function is. Now, piecewise defined functions can be graphed. It's perfectly fine to graph those, but basically what we have to do is we have to graph each piece separately, and we have to restrict the domain. So I'll show you how to do that on Desmos once. This is not something we generally do, but this is what you would have to do if you were doing this on Desmos. So let's say we started with our original piecewise defined function. F of x is equal to x minus 5 for all x values less than 2. And f of x is equal to negative x squared for all x values greater than or equal to 2. Again, I'll graph this on Desmos. We might have a companion video out there that graphs this on the TI-84 if you're interested in that. So the best way I know how to do this is just to graph both pieces. Graph f of x or y equals x minus 5. If I just type in y equals x minus 5, I get a line on Desmos. If I want to make sure that we restrict the domain to any x values that are less than 2, what I can do is I can just put set brackets and then say x less than 2. Okay. Now, this doesn't actually show the open circle. So if you want to actually show the open circle, the circle where we stop at 2, since we can't actually equal 2, then you just look at where this is. This is at the point 2, -3, and you can do a point 2, -3, and then change it to make it look like an open circle if we like. Okay, I'll make it a little bit bigger. So since we don't touch that point, you can just manually put in that point. But y is equal to x minus 5 for x less than 2. The other part of that piecewise defined function was negative x squared. So we write y equals negative x squared, and we want that, as you can see, here's what it looks like. We want that for any x values that are greater than or equal to 2. So normally it would be that entire parabola, but we're only looking at the parts from 2 and higher. And so that's that. Again, if you want to look and draw the point at 2, 4, since we have equal, 2, -4, since we have an equality there, we would probably make that a solid point. We would definitely make that a solid point. And then you can always, to make this look a little bit nicer, just make sure that you're using the same color for all parts of the graph. So that would be how we would define a piecewise defined function. And this is how you can get like gaps in the graph of a function. You can define it piecewise and you can have some gaps in between. So that's how you could graph a piecewise defined function. It looks like y equals x minus 5 when the x values are less than 2. It looks like negative x squared when the x values are greater than or equal to 2. I typically don't have people graph those piecewise defined functions by hand, but you could do that by hand in the exact same format we just did. It looks like the line y equals x minus 5 for the x values less than 2. It looks like the parabola y equals negative x squared for the x values greater than or equal to 2. So that's it as far as this section goes. We've looked at a lot of different things. We've looked at piecewise defined functions. We've looked at domains and ranges of graphs where we have restricted domain and ranges. We've looked at domain for various functions. Again, remember that the two things we are really concerned about in this class are domain errors where we're dividing by 0 or taking square root of a negative number. And so that's it for this section on domain and range of functions.